talking about some shapes today. We're going to talk about, Ben, are you hiding in your mask? We're talking about special parallelograms and trapezoids. So there are 3 different types of special parallelograms that, I hope we all have heard of before, at least 2 of them, or else we missed that day of kindergarten. However, we're going to learn about some different special properties that associate with them today. So the first special parallelogram that we are going to talk about is a rectangle. So if a quadrilateral is a rectangle, then it is a parallelogram with what? Who knows what makes a rectangle, Brock? Yeah, how many of them? 4, yeah, all of them have to be. So it's going to have 4 right angles, or you can put 90-degree angles if you prefer. So if we have a rectangle, we are going to have 4 right angles. Something else to think about as we talk about these shapes, they're parallelograms, right? And don't parallelograms have their own properties? Like opposite sides are parallel, opposite sides are congruent, things like that. All those properties are still going to apply. This is just like in addition to that. Rhombus. If a quadrilateral is a rhombus, then it is a parallelogram with, this one I don't know if you'll know or not, because rhombus isn't as common. Sebastian? Yeah, in this case, it ends up being that all 4 of the sides are congruent. So if a quadrilateral is a rhombus, then it is a parallelogram with 4 congruent sides. Both pairs of opposite sides in this situation end up being congruent. That makes all 4 of them congruent, and that makes it a rhombus. So all 4 of your sides here will be congruent. A square. If a quadrilateral is a square, then it is a parallelogram with 4 right angles and 4 congruent sides. So hopefully, I have no doubt that we all knew that. But what you might not have realized is that a square is both a rectangle and a rhombus. Okay, so a square is both a rectangle and a rhombus. There's kind of like this hierarchy of your shapes happening here. Everything is a parallelogram, right? Opposite sides are parallel, opposite sides are congruent, opposite angles are congruent, diagonals bisect each other. Everything has that going on. Then underneath that, you have rectangles. What's special about a rectangle? 4 right angles. You also have rhombuses. What's special about that? 4 congruent sides. And then if you take those 2 shapes and you combine them, you're going to end up with a square. So a square is going to have all the properties of a parallelogram, all the properties of a rectangle, and all the properties of a rhombus. It's like you took all of them, mixed it up in a blender. It's going to have everything. So yeah, square is going to have 4 right angles, 4 congruent sides. Both pairs of opposite angles and sides are congruent. Squares are kind of nice because everything ends up being equivalent for the most part. Questions about those shapes? Okay. All right, we have some theorems associated with these shapes. These theorems kind of serve as properties or like a way to prove something's a rectangle, a way to prove something's a square. So our first theorem, the diagonals of a rectangle are congruent. So now not only will they bisect each other, they are going to be congruent. Now, if that applies for a rectangle, what other shape is that going to apply for? A square, right? Automatically, something applies for a rectangle, it applies for a square. So the diagonals of a rectangle are congruent, that'll also work for a square. The diagonals of a rhombus are perpendicular. So if you had diagonals in this diagram up here, those diagonals would intersect to form 4 right angles. Okay, so those are going to be perpendicular. If the diagonals of a rhombus are perpendicular, what other shape has perpendicular diagonals? A square. Exactly. Each diagonal of a rhombus bisects two angles of the rhombus. In other words, that sounds a little weird. The diagonals are basically angle bisectors. Okay, so the diagonals serve as angle bisectors, which means your angles here are going to be cut in half. Okay, so your diagonals end up being angle bisectors. And again, that will also apply for a square. The midpoint of the hypotenuse of a right triangle is equidistant from the three vertices. We can draw a little diagram that goes with that. Now that has nothing, well, not that it has nothing. That theorem doesn't say rectangle, rhombus, square, parallelogram, anything like that in the theorem, right? However, sometimes when you have a diagram and you have a bunch of diagonals drawn in it, you'll end up with some right triangles. So that can be helpful for you to figure out some measurements. So what this theorem is saying is if you have a right triangle, the midpoint of the hypotenuse, so on your hypotenuse, let's say there's midpoint M. M is going to be equidistant from the three vertices. So let's say your vertices were A, B, and C. The distance from M to A is going to be the same as the distance from M to C is going to be the same as the distance from M to B. That's what that's saying. Okay. Does that sort of make sense, guys? Okay. If an angle of a parallelogram is a right angle, then the parallelogram is a rectangle. What actually ends up happening with that, if one angle is a right angle, aren't all the angles going to have to be right angles? Because think about it, if you have a parallelogram, opposite angles are already congruent, right? So that doesn't even kind of look like a rectangle. So if you have a parallelogram, one angle is a right angle, automatically the one diagonal from it's going to be a right angle. Also, if it's a parallelogram, your sides are parallel, aren't they? Does anyone remember what kind of angles are going to have to be formed here? If the top and bottom, or the left and right of your shape is parallel. It's an angle relationship that we talked about a while back. Logan? Well, they will be supplementary. They end up being same side interior angles. But yes, they end up being supplementary. So if one's 90, what's the supplement of a 90-degree angle? Another 90-degree angle, right? And then you can kind of work your way through. That's why everything has to be 90 degrees. Plus, too, if it's a quadrilateral, won't all the interior angles have to add to be 360? So, and that, which one am I at now? There we go. Last one. If two consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. What this is saying is if you have a parallelogram and the consecutive sides, those are the sides that are next to each other. Consecutive is like in a row, like consecutive days. Every parallelogram I draw gets worse. Okay, we'll deal with that one. So consecutive means the ones adjacent to each other or next to each other. So if it's a parallelogram, you already know that opposite sides are congruent, right? So if I tell you that the ones adjacent to each other, and I know this diagram's not drawn to scale, but that's okay. If I tell you the consecutive ones are congruent, that's what I mean. So for example, if this was 5 units and this is 5 units, if it's a parallelogram, don't the opposite sides also have to be congruent? Therefore, the top's going to be 5 units and the right's going to be 5 units. So those two consecutive ones being congruent, implies everything's going to be congruent, implies it's going to be a rhombus. Okay. So I made sure to throw some always, sometimes, nevers on here because this is a good always, sometimes, never chapter. My apologies. So, and the reason that it is because there's a lot of different properties, plus certain shapes have certain relationships to each other, right? Like a square is both a rectangle and a rhombus, things like that. You're going to see a lot of that stuff occurring. So let's try this out. People at home, are we good so far? Okay. Ashley, you didn't sound very confident, but I'll believe you. All right, so always, sometimes, or never. A square is a rhombus. Always, sometimes, or never. Logan? Always. I'm just going to put an A for always. Is that okay? Okay. Always, absolutely. A square has all the properties of a rhombus. A square is always a rhombus. Let me turn that around on you. Is a rhombus always a square? You'd have to say sometimes, right? So make sure you're careful with that. The diagonals of a parallelogram bisect the angles of a parallelogram. The diagonals of a parallelogram bisect the angles of said parallelogram. Always, sometimes, or never. What I would think about when you decode this, guys, isn't it just saying parallelogram? Any old parallelogram, right? Well, think about your parallelogram properties. Are the diagonals bisecting angles? Is that a parallelogram property? No. What shape is that a property of? You can look up above. I don't expect you to have it memorized yet. Logan? A rhombus. Specifically a rhombus, the diagonals bisects the angles, right? So if the shape is a rhombus, awesome. Yes, that's happening. But what if it's not a rhombus? Then is it happening? Yeah, no, we would put sometimes for this one. Okay. Because again, it only works if it's a rhombus. A good way to kind of think about if it's always or sometimes at least is think, since it's saying parallelogram, is this a parallelogram property? Right? If not, then you at least know it's not always. A quadrilateral with one pair of sides congruent and one pair parallel is a parallelogram. A quadrilateral with one pair of sides congruent and one pair of sides parallel is a parallelogram. This one's a little tricky. Logan? Why sometimes? Yeah, well, and with this one, if you think about your parallelogram theorems from the other class, if you have a parallelogram with one set of sides that's both parallel and congruent, isn't it a parallelogram? But look at your wording here. Isn't it just saying one pair of sides congruent and one pair of sides parallel? Is it saying it has to be the same side in this situation? No, this could be actually a trapezoid, is why it doesn't always work. This is saying you have a situation like this. One set is parallel, but maybe it's the other set that's congruent. That could end up being what's called an isosceles trapezoid, actually, which we'll talk about in a little bit. But that's why that one is sometimes. People at home were awfully quiet. We got quarantined, and then we left these poor 9 people hanging as the only people to answer questions. Make sure we answer some questions. Or at least try to. Okay, the diagonals of a rhombus are congruent. Always, sometimes, or never. The diagonals of a rhombus are congruent. So, diagonals being congruent. Take a look up at all the things we just defined. Which shape has congruent diagonals? A rectangle. A rectangle has congruent diagonals. Well, this is saying rhombus, though. So that's interesting. So if it says rhombus, but it's a rectangle property, is it going to be always? No. So we just have to then decide, is it sometimes or is it never? Well, think, are there any times where rectangles and rhombuses are interchangeable? It's a square. So do you think this would be sometimes or never? This one is going to be sometimes. This one is going to be sometimes. The reason it is sometimes is because what if this rhombus is actually a square? Isn't a square technically a type of rhombus? Yeah. So that's where that that comes in there. A rectangle has consecutive sides congruent. A rectangle has consecutive sides congruent. Look up at the definitions we just did. Which shape has consecutive sides that are congruent? It's one of the theorems we just talked about. A rhombus, okay. But this is saying a rectangle. But think about it, same thing like we just talked about. Is a rectangle sometimes a rhombus? Yes, when it ends up being what shape? A square. So we would say what, Sebastian? Sometimes. Adorable. Okay. Does that kind of make sense, guys? The rectangle and rhombus stuff can get a little tricky because you have to remember that it could also be a square. A rectangle has perpendicular diagonals. Think about what we've just been talking about. Yeah, it's sometimes because this is technically a rhombus property, but could it be a square? Yes, so sometimes. It is a lot of sometimes. Oh, I should do that on a test, make all of them the same thing. That could be fun. I don't think I would do that because I know that would have really stressed me out. So, part G, the diagonals of a rhombus bisect each other. The diagonals of a rhombus bisect each other. What shape has the rule that the diagonals bisect each other? Okay. You're not wrong. But there's a larger overarching shape that we've been talking about that has a rule that the diagonals bisect each other. Parallelogram. Okay. So diagonals bisecting each other is a parallelogram property. Is a rhombus a type of parallelogram? So is every parallelogram property going to apply to a rhombus? Yes. So what do we think? Always, sometimes, or never? Always. The diagonals of a parallelogram are perpendicular bisectors of each other. The diagonals of a parallelogram are perpendicular bisectors of each other. So they're bisecting and making right angles. What do we think? Why never? Well, is there a theorem that talks about bisecting? Like or perpendicular? Well, not a square, but a rhombus. Or not a, I mean, sorry, not a rectangle, but a rhombus. A rhombus has that property. But yeah, or a square. You could think about it either way. First of all, if it's a parallelogram, isn't the bisector part always going to be true? Yes. The perpendicular part is only going to be true when it is a rhombus or a square. So that's why this one is sometimes. Then why didn't you say it? Lies. All right. We got a proof. We are given parallelogram ABZY, and that ZY is congruent to BX, and that angle 1 is congruent to angle 2. We want to prove that ABZY is a rhombus. Okay, so first let's just go ahead, let's write down our given parallelogram ABZY. Segment ZY is congruent to segment BX, and angle 1 is congruent to angle 2. Now, if we are trying to prove that something is a rhombus, go look to our definitions and our theorems above. What are some ways that we can prove a shape is a rhombus? If it has 4 congruent sides, absolutely. That's really about it, because, well, I guess you could show that the diagonals are perpendicular, but in this situation, do we even have diagonals drawn? No. Okay, so we need to show that all 4 sides are congruent. So, in order to do that, take a look at what you're given. We're given some congruent sides. We're given some congruent angles. How could these things help us? Any ideas at all? Logan? Exactly. Yep, that is where I would go as well with that right away. So we are going to say that first. So segment BX is congruent to segment BZ. So segment BX is congruent to segment BZ. By the isosceles triangle theorem. Good. Why is that helpful? Why would that be helpful? Braden. Very good. So now we're going to know that BZ is congruent to ZY. That's great. That gives us that 2 of our sides are congruent. Before I write that down, though, why is that going to be helpful? Because it's important for you guys to kind of visualize your proof before you go and write it all down. So I like that. We're going to put that next. Why is that helpful? Why is saying that BZ is congruent to ZY? Why does that help us? And actually, why does that almost get us to exactly where we need to be? Logan? Exactly. And once we've shown that BZ is congruent to ZY, won't we have shown that 2 consecutive sides are congruent? So will there actually be anything else we need to do at that point? No. We'll have already shown it's a rhombus. You don't have to actually go through the process of all 4 sides because you've shown 2 consecutive. So good. So we're going to use our transitive property. We're going to say that segment ZY is congruent to segment BZ. We're using the transitive property for that because both parts here were congruent to BX. Okay, so therefore they're congruent to each other. Let me rewrite this. Oh, didn't mean to highlight it. There we go. Okay, so BZ, that is the transitive property. And then what we are going to say is we're actually done. We can go to our final step. A, B, Z, Y is a rhombus. Now, there's not like a cute little short name for this theorem, so just abbreviate and shorten as you see fit. Honestly, write a short if-then statement, right? So I'm going to say if, let me move over here because I can only write so small with this stylus. So I'm going to say if 2 consecutive sides are congruent, then the parallelogram, and I'm literally just going to do my little parallelogram symbol just like you would for a triangle, then the parallelogram is a rhombus. Questions about that? People at home, any questions about that? No? Okay. Onward. Oh. No, it would be, you would have to like almost draw a parallelogram with like the little 4 congruent sides. You know what I mean? Like I would know what you meant if you did it. Your picture would have to be very clear, you know? Yeah. Really the only ones that have their own symbols are circles, parallelograms, and triangles. Okay. So moving on to the back, we are going to talk about trapezoids. So for a trapezoid, our definition is if a quadrilateral is a trapezoid, then it has exactly one pair of parallel sides. Exactly one pair. So can it have 2? No, exactly one pair. In this situation, it would be the top and the bottom here. Is it always going to be the top and the bottom? No, depends on how your picture is drawn. Okay. But in that situation, that would be your parallel sides. These are called the bases. So the bases of a trapezoid, those are the parallel sides. So this is a base and this is a base. Sometimes people tend to be like, oh, the base is on the bottom. Not necessarily. Depends on how your picture is drawn. The base is the parallel sides. The legs of a trapezoid, those are just simply the other 2 sides. So this would be a leg and this would be a leg. So those are the legs of your trapezoid. Very similar to like when we talked about an isosceles triangle, right? Just like there are isosceles triangles, there are isosceles trapezoids. Refresh my memory. What's an isosceles trapezoid? Oh no, I'm sorry. What's an isosceles triangle? What makes a triangle isosceles? Yep, it is a triangle with 2 sides that are congruent, therefore 2 angles are going to be congruent. So guess what an isosceles trapezoid is going to be? Yep, exactly. It's a trapezoid with 2 sides and 2 angles that are congruent. Kind of a way to look at this is imagine that I'm going to erase this, so don't draw it. What if you kind of took your trapezoid and extended the sides upward? Doesn't it kind of form a triangle? It's like you took a triangle and chopped the top of it off. All right. I know. So the world's not nice, Sebastian. Sometimes you got to chop the top off of a triangle. All right. So that's kind of why those properties still work for this. And a lot of the things are going to be the same. So if a trapezoid is isosceles, then it has congruent legs. So you would still have your parallel bases, and then you would have your congruent legs. And then sometimes what you're going to see in trapezoids is a median. If a segment is a median of a trapezoid, then it joins the midpoints of the legs. Very similar to the mid-segments we talked about. Sometimes they're called mid-segments, sometimes they're called medians, depends on the diagram and exactly what the problem's asking you. But remember when we talked about mid-segments in a triangle, they connected the midpoints on either side? Same thing's going to happen here. So if your trapezoid has a median or a mid-segment, then it just connects the midpoints. So I'll actually draw a different picture here. So you would have your trapezoid and your mid-segment or your median would just connect your 2 midpoints. So you would have congruent parts on either side there. And just like before with the triangle mid-segment or median, it's going to be parallel to your bases as well. Okay, so it's going to cut both sides in half and be parallel to the base, which we talk about in our next theorem. So a couple theorems. The base angles of an isosceles trapezoid are congruent. So just like the base angles in an isosceles triangle are congruent, the base angles in an isosceles trapezoid are also congruent. Oh. Sorry, one second. There we go. So these base angles are going to be congruent. And it's only, well, so when we talk about the congruent base angles, how many sets of base angles do you think you have actually? Let's take a closer look at this picture. Where am I going to have base angles in an isosceles trapezoid? How many bases do I have in a trapezoid? 2. So how many sets of congruent angles do you think you're going to have? Well, technically there's 4 angles, but 2 sets of them will be congruent. So these 2 will be congruent, and then these 2 will be congruent. I just really struggle to draw an arc with this thing. There we go. Okay. Okay, that's the best I can do. Another thing to mention, it's not a theorem on here, but think about what we've learned. Your bases are parallel, right? Don't parallel lines form congruent or supplementary angle relationships? So think about with the rectangle, if one angle was a right angle, they were all right angles, right? Because the opposite ones had to be congruent, but didn't the ones along the same side have to be supplementary? Same thing's going to happen here. This time, you're going to have your congruent base angles, so on either side of your base, but then the ones in between your bases are going to have to be supplementary. So for example, if this angle is 100 degrees, this angle is going to have to be 80 degrees. Okay. All right, and then our last theorem is for our median, which we kind of already talked about. The median is always going to be parallel to the base, same ideas with our mid segments, and its length is half of the average of the base lengths. When we were dealing with our triangle mid segment, we would have our triangle, and in this situation, the median was just half of this side it was parallel to. So for example, if this was 5, that was 10, right? This is a little different though, because don't you have 2 bases? In a triangle, you'd only have 1 base. In an isosceles trapezoid, you're going to have 2 bases, so you have to take both of them into account. So you would have to take the average. How do you take the average? Add them up, and in this situation, divide by 2. Okay, and we do 2 examples of that down below, so we'll see exactly what that looks like. So again, to find your median, you basically add up your base lengths and then cut it in half. Add them up, divide by 2. There's a few different ways to set up those equations. Any questions about our properties or theorems? Ben? It would be if it's an isosceles trapezoid, but it doesn't have to be isosceles. For example, you could have a trapezoid that looks like this, right? And then in that situation, then they most likely would not be congruent on the left versus the right. Does that answer your question? Okay. Logan? Yeah, it should be. That'll be easy to do when you're given like nice whole numbers. More challenging to deal with if I'm giving you like expressions and stuff. But yeah. Yeah, you're basically finding the middle, right? So like if your base has a length of 10 and your other base has a length of 12, it's 11. Yeah. All right, so let's look at a few examples then. The diagram shows a trapezoid with a median. Solve for x. So this, I trust that if it's just whole numbers, we can figure it out, right? So that's why I wanted to make sure I gave you guys one with some expressions. We got to do a little bit more algebra with this. So in this trapezoid, here is your median, right? It's this segment in the middle here. So my theorem tells me that the mid-segment or the median is half of the sum of the two bases. It's the average of the two bases. So there's a few different ways you could set up an equation for this. Does anyone have any ideas how we could set up a good algebra equation for this? Yeah, the segments. Yeah, we could definitely add those two bases, divide it by 2, and then set that equal to the median, right? You could do that in multiple steps if you want, or write it all at once if you want. It's completely up to you. I'm going to show you how to do it with one equation, and if you wanted to split it up into smaller parts, you definitely can. So I'm going to say that my mid-segment, which is 2x plus 4, equals, and if you guys prefer to use a fraction like a half, you could put a half in the front. I'm more of a divide by 2 type of person. I assume probably most of you are as well. Fractions sometimes freak people out. So then what I'm going to do is I'm going to add 3x plus 2 plus 2x plus 1, and I'm going to put it all over 2. Again, you are absolutely welcome to do this in multiple steps if you prefer. I'm just showing you a way to get it kind of all done at once. Now, don't worry about that divide by 2 yet. We're going to deal with that at the end. So then you just simplify. That's going to give me 2x plus 4 equals 5x plus 3 over 2. Now, with this strategy, if I go ahead and I simplify my left-hand side, or my right-hand side, I'm sorry, by 2, what's going to happen? I'm going to have decimals. Is that okay, though? Are they going to be just 0.5s? Yeah, that's fine. So if that's what you feel more comfortable with, that's what I would do. Personally, that's probably the route I would take. You're actually less likely to make a mistake. Does anyone know, though, an alternative way you could keep simplifying this? If you wanted, Ben? Yeah, you can 100% also multiply the other side by 2. What's the thing you got to be careful about, though, if you do that? You know? Does anyone know what you maybe have to be careful about? It's a good strategy. You just got to be cautious. Lucas? Possibly negatives. What else? So when you multiply both sides by something, do you just get to pick and choose what you want to multiply? You got to make sure you multiply all of it. When you multiply both sides by 2, wouldn't it be really easy to just multiply the 2x by 2 and forget about the 4? Yeah, so if you want, you can 100% multiply both sides by 2, but make sure you distribute. That needs to become 4x plus 8, okay? Or if you prefer, you don't want to mess with that, then just use some decimals. I mean, everything, it's just going to be dividing by 2, so you shouldn't have anything strange. So you would have 2x plus 4 equals 2.5x plus 1.5. Then I'm going to subtract my 2.5 over to get negative 0.5x equals, and I'm going to subtract my 4 over to get negative 2.5. And then I'm going to divide that. I don't trust myself with decimals in my head at the end of the day. That should give you 5. Right. 100% there's more than one good way to set this up. This is just one suggestion. Okay, so do what you're comfortable with. The one that's like this on your homework, I gave you odd ones, so you'll be able to check and make sure you did them right, okay? All right, number 2, trapezoid ABCD has mid-segment BE. If AD is x plus y, BE is 20, and CF is 4x minus y, find x and y. Everybody's favorite kind of problem. Uh-oh. So something that could be helpful to you would be to draw a diagram. So I'm going to. Here is my trapezoid. My trapezoid is A, B, C, D. Anytime you label something like that, make sure you go in alphabetical order. And then my mid-segment, oh wait, you can't do that. Wait, hold on. Let me make sure I wrote that down right. A, B. What did I do weirdly? I just messed up. I think it shouldn't be trapezoid A, B, C, D is what I did wrong. Your picture should look like this. My bad. Your picture should look like A, D, B, E, C, F. So my mistake, it should be trapezoid A, D, F, C, like that. Okay. So this is saying that AD is x plus y, BE is 20, and CF is 4x minus y. Find x and y. Okay, so this is definitely going to be a system of some sort, right? So when we set up our system, we need to think of some different equations we could set up here. What's one equation you could set up for this? Yeah, that would be one you could set up. Maybe. Ben? The strat. Sorry, really distracted and didn't realize what that meant for a second. The strategy, yes, continue. Uh-huh. The whatever it's called. Okay, so I like both of these, but I think those end up being basically the same equation. If I'm understanding you guys correctly, Braden. Yeah, okay, so good. That's definitely one equation we could set up. I like that as well. So again, there are a few different strategies you could use. Someone suggested the 1/2 one. I think if we do that, we should end up getting, I think I agree with you with that one, Sebastian, that we should get a nice equation. And then we'll also go with that strategy from Braden, and we'll see what we end up with, right? So let's start with that one. So we're going to add them up. And then remember, your mid-segment is half, right, of the two added together. So your mid-segment equals 1/2. This was what you were saying to do, right, Sebastian? Your mid-segment equals half of x plus y plus 4x minus y, and then I'll throw my divide by 2 over there. So I will have 20 equals That'll give me 5x, and then my y's are actually going to cancel, right? Divided by 2. And then could you put that as a 2.5 if you want? You could. This is one, though, that I would probably do that distribute. I would multiply both sides by 2 instead. So you should get 40 equals 5x, and x should equal 8. Okay. So that's nice because now we already have one of our variables, right? Now we just have to come up with an equation to solve for the other one. So what we could do here, well, we already have an equation, don't we? Could we just substitute this in? Yeah, we could just substitute it in. And Braden, if you wanted to do the 40 equals, that's also a good equation for it too. That would be the same as this, just you would instead of, you would have multiplied by 2 at the start. Does that make sense? Yeah, okay. So either way, so now I'm just going to take my original equation, and I'm actually going to plug it in the way Braden said, because I don't want to deal with that divide by 2. I'm going to rewrite this as 40 equals x plus y plus 4x minus y. Oh, I'm sorry, 4x, not 4y. And then I'm going to plug that in there. I'm just rewriting it. You don't have to. This is more just so you guys can see what I'm doing. Okay. And I'm going to take this x and I'm going to plug it in everywhere where I see x. So that's going to give me 40 equals 8 plus y plus 4 times 8, which is 32, minus y. Oh, wait, that doesn't work out. Why doesn't that work out? Because they're just going to cancel each other out. So what are we going to maybe have to do instead? We need to make a different equation. Yeah, I didn't think that through properly. Wasn't that, we already used your strat. We already used your strat, so we need a different equation to plug this back into. So we need a different equation. Any ideas on a different equation, Logan? Yeah, very good. So you said to multiply AD by 2? That's right, Logan, you said to multiply AD by 2? Yeah, that's exactly what you should do. So yeah, so what we're gonna do here is do 2 times x plus y equals 20. Good? Yeah. And then we're going to distribute or divide by 2, however you feel like doing it. But I'm going to turn this into 2x plus 2y equals 20. I'm going to plug my 8 in there. So 16 plus 2y. Yes. Right now I'm using line 80. AD is half of CF. Yes. Oh, because that also works. I thought that was what you said at first. That was the way I had done it originally. Which way did you say, Logan? Say that one more time. But you plugged that in where? Oh, so you plugged it in where, here? Oh, you plugged this in. Oh, you could also do that. What did you end up going all the way through it? Did you end up going all the way through it yet? Okay. Well, I guess let's see how it works out. Because we should get 2. So let's see if we get 2. All right, so let's see if we end up getting 2. So you plugged 4x minus y in here, like that? Okay, so let's see. So that'll give you 2x plus 2y equals 4x minus y. So 16 plus 2y equals 32 minus y. Add your y over, that gives you 3y. Oh, I don't think that works. Subtract that, you get 16. Now we're going to get some weird decimal. Yeah, sorry. It was worth a try, though. I was curious. So the only other way I can think to do this, and let me know if you guys think of something else, because there's always more than one good way. So I'm willing to try a few different things and see what works. But what ends up happening here is that if you take 2 times your base in this situation, so 2 times x plus y, that actually does end up equaling 20 in this scenario. And it's actually, I think part of that is because of, yeah, you guys, that's my fault on this one. It was a picture that had a little bit more going on to it that I didn't think to put in the directions. So that would be 2x plus 2y equals 20. And then you would have 2 times 8 plus 2y equals 20. So 2y equals 4 and y equals 2. I was actually trying to simplify the problem, and in the process I made it more challenging. The diagram in your textbook that this problem actually goes with looks like this. Yeah, it's a triangle. Good job, Ben. Where this is AD, this is BE, and then this is CF. So, and I neglected that part when I was writing the problem down, that the measure of AD is also going to have to equal twice the measure of BE because of the theorems we learned last class. So I need to make sure I fix that picture. Does that make more sense now? That was my bad. All right, so last thing, number 3. Give the best name for the special quadrilateral ABCD if it satisfies the conditions stated. You guys can always do a sketch for this. That's what I'm very visual. That's what I need. If you want to, great. If you don't want to, that's fine too. I'm just going to kind of generically draw myself a little square here. This is A, B, C, D. It is telling me that AB is parallel to CD or DC, and that AB is perpendicular to AD. So if it's giving you one set of parallel bases and then one right angle. Logan, why a rectangle? You're falling into the trap, Logan. It's not a square. It's not a rhombus. How many? Well, that's the issue. Is this a parallelogram? Is this a parallelogram? Logan, is it a parallelogram? Why is it not a parallelogram, Logan? Well, but what would it need? Like, what else would this need to be a parallelogram? 2 sets of parallel sides. You fell into the trap. It needs 2 sets of parallel sides. If this problem has 2 sets of parallel sides and one right angle, then is it a rectangle? Definitely. This one's only giving you 1 set of parallel sides. This is a trapezoid. I mean, yeah, it was like the 5th shape you said, but I guess you said it. All right, part B. Does that make sense, guys? Okay. Part B. So here, let me draw my little generic shape again. AB is congruent to C or DC, and AD is congruent to BC, and AB is also congruent to BC. A lot happening here. A lot of things are congruent, so those are also congruent. Okay, so you know that opposite sides are congruent, right? So that means it's going to be some type of parallelogram. But in addition to that, it's telling you that AB is congruent to BC. So what kind of parallelogram is going to have consecutive sides congruent like this? A rhombus. This is a rhombus. People at home, are we still there? Are we still hanging on? Okay. All right, cool. So for part C, here's A, B, C, D. It says AC is congruent to BD. So those are your diagonals. It's giving you congruent diagonals. And AC and BD are perpendicular bisectors of each other. Well, which shape has a property that the diagonals are congruent? Okay, a rectangle. Which shape has a property that the diagonals are perpendicular? The angles, yes, but this is saying the diagonals themselves. So yeah, the diagonals are congruent, that's a rectangle. The diagonals are perpendicular, that's a rhombus. What do you get if you take all the properties of a rectangle and a rhombus? You get a square. All right, last one. AB is parallel to DC, and BC is perpendicular to AB, and AD is perpendicular to AB. All right, so now this one, it's giving you one set of parallel sides, but it's also giving you two right angles. Huh. Okay, so Ben and Sebastian thinks it's either a rectangle or a square. Can we narrow that down to one? Why just a rectangle? Yeah, they're not saying that any of the sides are congruent. Now, this is where you might be like, but in part A, there was only one set of parallel sides and it was a trapezoid. But what's different about this scenario? It's giving you two right angles this time. And if you know that these sides are parallel, then you're going to have supplementary angles, right? Your same side supplementary angles. So this is also going to have to be a right angle, and that's also going to have to be a right angle. It is a rectangle. Good.